Hello everyone. Today I introduce a project and presentation. Number one, optimization of indium gallium arsenide, indium arsenide photodetectors with super lattices. Number two, highly sensitive and self-powered UV photodetector based on GaN polystyrenosulfonate polyaniline heterojunction. Number three, effect of platinum doped on the photocurrent of MSM photodetector. Journal list. These journals from references now superlattices and microstructure materials, letters, journals of physics conference series. Journal 1, optimization of indium gallium arsenide photodetectors with super lattices. Okay, executive summary of journal 1. In this study we may know that the performance of the indium gallium arsenide superlattice photodetector can be improved by changing the position and thickness of the electron barrier in the absorption layer. Indium gallium arsenide superlattices inserted into the intrinsic layer of the PIN structure with the optimal positions of the superlattices. This will reduce the dark current and improve its performance. The main problems are lattice mismatch and strain imbalance of the photodetector, with gallium arsenide used as a substrate for the band gap of indium gallium arsenide, which can be changed from 1.7 electron volt to 1.1. Number two, research methodology of optimization photodetectors with the superlattices. PIN type indium gallium arsenide photodetector with gallium arsenide as substrate to reduce mismatch. Thin indium gallium arsenide superlattice optimal position that inserted in the edge of the intrinsic layer on top of the absorption layer, and increasing the thickness of superlattice indium gallium arsenide. And number three method, increasing the number of inserted superlattice layers. To avoid adverse effect, the carriers are very sensitive to the diffusion process in the active region in photodetector, and finally reduce dark current. Now increasing the effective barrier height, resulting in electron resulting to reduce the dark current. And finally, the performance of the number three, results and discussion of journal 1. Figure 1 shows the PIN type indium gallium arsenide ALAS photodetector with superlattice electron barrier model, where the P layer and N layer are indium aluminum arsenide. The intrinsic layer is indium gallium arsenide with an indium gallium arsenide over indium arsenide superlattice structure. The thickness of the P layer is 0.55 micrometer, which is sufficient to meet the required electric field and can generate the most carriers. The thickness of the intrinsic layer was 1.5 micrometer. This thickness is sufficient to be or to embed the required superlattices and maintain. For PIN structured photodetectors, carriers generated by incident sunlight will be absorbed by the intrinsic layer, part of which provide the current, and the other part are lost due to recombination. In order to increase the number of collected carriers, a superlattice that is as thin as possible is used so that the carriers can pass through inbuilt in electric field. As shown in figure 1b, some special physics or some special physical models must be selected. Diffusion models and carrier generation composite models, impact ionization model, and interband tunneling model. As shown figure 2, the inserted superlattice layer is a 0.1 micrometer thick indium gallium arsenide superlattice barrier structure, and the thickness of each layer in one period is 10 nanometer. We can change the position of the inserted superlattice layer, which is divided into an upper layer, a middle layer, and a lower layer. The upper layer is 100 nanometer away from the P layer. The middle layer is 400 nanometer away from the P layer, and the lower layer is 700 nanometer away from the P layer, as shown in figure 2. When we change the number of inserted superlattice layers and dividing them into 10, 20, and 30 layers, one period includes 10 nanometer indium gallium arsenide and 10 nanometer indium arsenide, as shown in figure 3. The dark current is 6.42 phi. 6.42 multiply 10 sub minus 5, 3.18 multiply 10 minus 5, and finally 1.55 multiply 10 minus sub minus 5 respectively at minus 0.8 voltage. The results show that when the superlattice layer is 30 layers, the dark current is significantly reduced, which narrates the positive effect of increasing the number of layers. And when we change the thickness of the inserted superlattice layer into 5 nanometer, 10 nanometer, and 15 nanometer, the superlattice includes 10 layers, as shown in figure 4. Okay, now journal 2, highly sensitive and self-powered UV photodetector based on gallium nitride over poly polystrinosulfonate polyaniline heterojunction. Number 1, executive summary. In this paper, we study the ultraviolet photodetectors to know that they have highly sensitive and self-powered and used in wide applications like monitoring, UV imaging, and flame sensing. The photodetectors embrace PIN junction structure, consist of a layer of molecular beam epitaxy MBE grown N-type GAN, a layer of spin-coated high-resistance polystrisulfonate PSS, and a layer of dip-coating P-type polyaniline PANI. When the optimized thickness of PNI and PSS increases, the photocurrent increases and reaches the maximum value and gradually decreases with further increase of their thickness. This optimized device can work and output photocurrent at 0 voltage bias voltage without any external power and have fast response to 365 nanometer UV light, indicating that is self-powered device. Now, in research methodology, the GA. Number 3, results and discussion of Journal 2. Figure 1 is schematic illustration of the photodetector. The device of GAN over PSS PANI hybrid heterojunction structure was fabricated on the C-sapphire substrate. And figure 1b shows the cross side of the device. It demonstrates that the thickness of GAN, PSS, and PANI are about 165 nanometer, 3.9 LM and nanometer or LM and 8.93 LM for the optimized device. Respectively, the top view of PANI, figure 1C, demonstrates the PAN layer is composed of nanowires of diameter about 105 nanometer. Figure 1 and finally figure 1D shows the top view of the MBE grown GAN. A hexagonal mosaic structure can be found in the plane, indicating the GAN has grown under GA-rich conditions and has undergone two-dimensional growth pattern epitaxy. This morphology implies the stress relief and low defect density in the sample. The UV via absorption spectra of GAN curve 1 and GAN PSS PANI composition curve 2 are shown in figure 2a. It indicates that GAN has a sharp absorption peak at about 358 nanometer. The absorption spectrum of the GAN PSS PANI multilayer has an absorption platform at the range of 368 to 446 nanometer. And figure 2b displays the spectral responsivity of the optimized device, exhibiting visible blend characteristic. Figure 2c shows the FTIR spectra of the PANI. The main characteristic peaks demonstrates that the PANI is doped by H2SO4. Now the IV curves present weak rectifying characteristics as shown in figure 3a, which are nonlinear and asymmetric. This behavior may be ascribed to the structure of a PIN like heterojunction between GAN, PSS, and PANI. The similogarithmic plot of current as function of voltage was shown in the inset of figure 3a. The ideality factor N has been calculated from the following equation: N equal Q over K sub B multiply T dV over dlni, where I is the corresponding current, V is the bias voltage, T is the absolute temperature, K sub B is the Boltzmann constant, and Q is the elementary charge. The value for ideality factor was found to be 6.6. The high value for ideality factor in our case indicates existence of trap-assisted tunneling current leakage defects at the interface. Figure 3b and figure 3c reveal the IV characteristics of the devices in different PSS thickness and PANI thickness, respectively. It is demonstrated that the ALGAN, PSS, PANI, AG devices have distinct UV photosensitivity. The photocurrent is varied with PSS and PANI thickness. Moreover, these devices can output photocurrent at 0 V bias voltage, indicating that it is a self-powered device. Now figure 3D is the IT curve of optimized photodetector. The photocurrent is stable in 5 cycles and reaches its peak immediately when illuminated with UV light at each cycle. It also indicates that the peak photocurrent 2.05 microampere and the current in dark is about 4.45 nanoampere. The rise time and the decay time of the photodetector, which were estimated to be 60 milliseconds. Figure 3 shows IT curves of the photodetector as function of PSS thickness. It indicated that as the thickness of the PSS increases, the photocurrent increases and reaches the highest value of 2.05 microampere with PSS of 3.90 micrometer, and then decreases gradually. The photocurrent of the device with optimized PSS thickness is about 9 times of that without PSS. PSS layer can functionalize the surface of GAN and PANI to form the intimate of heterojunction, so enhancing the responsibility of the device, which acts as a high resistance layer like the I layer and NPIN junction diode, and widens the depletion zone, therefore improving the photocurrent of the detector. The proper thickness of for PSS is 3.9 micrometer in the device. Thicker PSS layer may affect carrier transport, causing the decrease of photocurrent. Now figure 3F displays I with change of T curves of the photodetector as a function of PA and I thickness. It demonstrates that the photocurrent increases sharply to 2.05 microampere with the increase of thickness of PANI to 8.93 micrometer and then drops gradually. This phenomenon could be explained by the following reason. When the thickness is under 8.93 micrometer, the increase of the thickness leads to more sufficient contact between PAN particles and hence a lower resistance, which is favorable to carrier migration in PANI particles. But when the PANI thickness is above 8.93 micrometer, that transparency suffers, leads to the transparency suffers, resulting in photocurrent drop. Now, journal 3 effect of PT doped on the photocurrent of MSM photodetector. Number 1, executive summary. In this paper, we will know the difference of MSM photodetector performance in comparison between undoped and doped PT platinum atom. The fabrication of MSM photodetectors with PT doping is different process for atom doping and diffusion process. The PT atom doped in backside of substrate and use RTA process at 800 centigrade for 15 minutes. The metal finger spacing between metal contact at bias voltage 10V and after doped with PT atom. The capacitance voltage becomes higher and photocurrent increases. The positive effect of PT atom that the photo effect of device doping exhibit high photocurrent around 4.25 to 4.37 times from non-doped condition. We conclude that the PT atom helps to increase the performance of the MSM photodetector and develop it. Research methodology of journal 3. Okay, cleaning in silicon 100, thickness 400 micrometer, resistivity 7 to 20 ohm centimeter with DL water and ultrasonic for 5 minutes. And doping platinum atom backside of substrate. Number 3, annealing by using RTA process at 800 centigrade for 15 minutes. Coating AL on top of silicon and photolithography and open active area. Sinitering with 800 centigrade in nitrogen environment. Last step for checking adhesion of metal contact by using 3M sticker. Stick with contact and pull off. Finally, device after fabrication, both undoped and doped will measure capacitance voltage CV characteristics in dark environment by using tooling HP4156B by bias voltage step 0.1V, sweep from -10 to 10V. Then device will measure photocurrent by exposing light with various intensity from 5,000 to 25,000 lux. Step 5 lux. Result and discussion. Figure 1 shows MSM photodetector bi-undoped P atom. The picture shows spacing between metal contact around 40 micrometer and finger distance around 50 micrometer, as seen in research methodology. Figure 2 shows MSM photodetector doped with PT atom in backside of substrate. And figures 4 and 5 show photocurrent of device. The light exposed on device by distance around 5 cm with various intensities of light starting from 5,000 lux to 25,000 lux, increased by 5,000 lux per step. From these results, photocurrent has increased from 19.87 to 86.54 microampere at 5,000 lux, and photocurrent has increased 4.35 times after doping PT atom. Results of photocurrent doped by PT atom has increased around 4.25 to 4.37 times at light expose of 10,000 and or 10,000 to 25,000 lux. Now, table 1, photocurrent of device by various light intensity. Table 1 shows photocurrent ratio between BT doped and undoped MSM. The ratio after doped PT atom photocurrent was significantly higher. That helps in device performance improvement. The PT atom may create trapping center between valence and conduction band that helps to generate photo effect in MSM photo device. Now, overall comparison between 3 journals. Journal 1, optimization of indium gallium arsenide photodetectors with super lattices. Have high indium INGAS photodetectors covering the short wave infrared. The indium gallium arsenide detector shows lower current density and high detectivity at room temperature, and it used into important application in remote sensing such as environmental monitoring and night vision. Owing to the lack of nature lattice mismatched substrate for the high indium gallium arsenide, a high threading dislocation density is generated and has high dark current, so it needs to insert the super lattice layer to reduce the dark current. And journal 2, highly sensitive and self-powered UV photodetector based on GAN polycitrosulfonate and polyaniline heterojunction. The ultraviolet photodetector is smart, flexible, self-powered, and intelligent. UV photodetectors are urgently needed in health and infrastructure, environment monitoring, and unattended stations. GAN has many advantages, such as wide band gap of 3.5 electron volt and high carrier mobility among inorganic materials, and polyaniline PANI is a promising organic p-type semiconductor materials and polymer for optoelectronic devices, which are cheap and easy to prepare. Journal 2 Effect of PT doped on the photocurrent of MSM photodetector. Due to the wide bandgap of III nitrides like GAN, E9 equal 3.5 electron volt. These semiconductors are the most promising candidates to prepare visible blend ultraviolet UV detectors. Nevertheless, the lack of good quality p-type material and low resistance ohmic contacts are the reason to choose metal semiconductor metal MSM structures as first option to fabricate UV photodetectors. And the benefit from PT doped on the photocurrent of MSM photodetector is improving the light response. Now, overall conclusion. Journal 1 conclusion. The improvement of the performance of the INGAAS over INAS superlattice photodetector by reducing the dark current depends on three effects. Number one, the position and period and thickness of indium gallium arsenide superlattices on the current. Conclusion of Journal 2 that the photocurrent shows the tendency to increase first and then decrease with the increase of PSS and PANI thickness. Conclusion of Journal 3 PT Atom works on increased MSM photodetector performance and it constitutes for development of MSM doped with PT atom by increasing the photo. Finally, summary. My preferred journal is the second journal. That is highly sensitive and self-powered UV photodetector based on GAN polystyrene sulfonate and polyaniline heterojunction. Because first, the materials and polymer that used in this experiment are of low cost and easy to prepare and give a significant improvement in performance. Second, the journal addressed the great advantage of UV photodetector that the optimized device produced a photocurrent rapidly without any external power supply, self-powered. This feature of UV photodetectors widely used in optoelectronics applications. Third causes the experiment was supported with more details, figures, explanations that showed increasing and then decreasing of the photocurrent with increasing of PSS and PANI thickness. Now thank you very much to listen me and best regards.